Calorimetry is the study of measuring an energy transfer, or heat, by observing temperature changes. There are two conditions that we'll see in general chemistry: constant pressure and constant volume. In this lab, we'll work at atmospheric pressure, thus constant pressure. We'll study two processes. We'll find the delta H of neutralization for a strong acid-base reaction, and find the delta H of hydration for the dissolution of a salt. Let's start with the acid-base neutralization. Here is a classic calorimetry experiment where hydrochloric acid is neutralized by sodium hydroxide to yield sodium chloride and water. Along with this balanced equation, we have the change in enthalpy, or delta H. This is the equation that we'll use. Delta E, or Q as heat, is equal to the total mass of the mixture, or solution, times the specific heat times the temperature change. Recall from thermochemistry that at constant pressure, the heat is the enthalpy. Let's take a brief look at the experiment and return for our calculations. For the acid-base neutralization, I'll measure 75.0 milliliters of each, a 2-molar hydrochloric acid solution and sodium hydroxide solution. I'll transfer each solution into the respective labeled beaker and place a watch glass on each beaker to avoid evaporation, which can change the concentration of the solution. Here is my coffee cup calorimeter. The styrofoam cup is a good insulator and works nicely for our data collection. The plastic lid has entry points for a thermometer and stirring rod for mixing. I'll first transfer the hydrochloric acid into the calorimeter and measure the initial temperature, 21.0 Celsius. Before transferring the sodium hydroxide, be ready to stir the solution. I'll next transfer the sodium hydroxide solution and stir. You'll notice the temperature quickly increases, indicating an exothermic reaction, where heat is evolved or released in the reaction. I'll continue stirring until the maximum temperature is reached, in this case 35.0 Celsius. Let's look at the calculations for this experiment. For this equation, M is the total mass. Recall, I use 75 milliliters of each, the hydrochloric acid and the sodium hydroxide solutions. These solutions are mostly water, so I can reasonably assume that the density of water is about 1.0 grams per milliliter. Thus, each solution is about 75.0 grams. So the total mass will be 150 grams. I put a decimal here to signify the three significant figures. Next, since the solutions are mostly water, we can again reasonably assume that the specific heat is just the specific heat of water. So I'll use 4.18 joules per gram per degree Celsius. In chemistry for engineers or some other sciences, you might use calories as a unit of energy. This would be 1 calorie per gram per degree Celsius. In this case, we'll use joules. This is what we usually use in chemistry. And finally, the change in the temperature is the difference between 35.0 degrees Celsius and 21.0 degrees Celsius from the experiment. So this value right here is 14.0 degrees Celsius. Before calculating, the sign here is going to be negative. This is important. Recall the temperature increased, meaning that this reaction is exothermic. Heat is coming out of the reaction and increasing the temperature of the surroundings, or I'm measuring the temperature change. This equation gives a heat change of negative 8,610 joules, or negative 8.61 kilojoules. Next, it's common to report the change in enthalpy in kilojoules per mole. In this lab, we'll report this as kilojoules per mole of water produced. I have other videos on solution stoichiometry that I'll link to. Briefly, the experiment is set up so that there is no limiting reactant. All the reactants react or are consumed in the reaction. You will see here we use 75 milliliters of each solution. Each solution is 2 molar. I convert here to the moles of each reactant. Then I convert to the moles of water produced. You can see that for each reactant, the moles of water produced is identical. This means there is no limiting reactant. In other words, the maximum moles of water produced for each reactant is 0.150 moles. Let's find the kilojoules per mole of water produced. Negative 8.61 kilojoules divided by 0.150 moles of water equals a negative 57.4 kilojoules per mole. Generally, the accepted value for the strong acid-base neutralization is right at 56 kilojoules per mole. So let's find a percent error. So I'll take the absolute value. I'm just looking for the difference here, which is 1.4. We'll divide that by the accepted value times 100. And to two significant figures here, this is 2.5% error, which is a reasonable error. Now, let's look at the enthalpy of hydration. For the enthalpy of hydration, we'll use the salt potassium nitrate. Notice the phase is the solid phase. This will dissolve in water to produce potassium nitrate aqueous. We'll need to find the enthalpy of hydration. For this experiment, I'll measure 75.0 milliliters of deionized water and transfer the water to the calorimeter. Next, I'll tare a weighing boat, then measure about 5 grams of a salt to the nearest milligram. In this example, I'll use potassium nitrate. The mass here is 5.007 grams. I'll measure the initial temperature, 21.4 Celsius in this trial, and add the salt. It is very important to stir vigorously to dissolve all the salt. You can have the lid off for this trial so you can see the salt in the coffee cup. You can see the temperature decreases. This is an endothermic process. Heat goes from the water into the salt to dissolve it. From the salt's perspective, or the system, this is endothermic. Continue to stir until all the salt is dissolved and read the final temperature. In this trial, the final temperature is 16.2 Celsius. Now, let's look at the calculations. Again, our mass is the total mass. In this case, we used 5.007 grams of the salt, and this is dissolved in 75 milliliters of water. Again, for 75 milliliters of water and assuming a 1.0 gram milliliter density, we can assume 75.0 grams of water. This gives us a total mass of 80.01 grams. I'll use the specific heat of water. And the change in temperature is just the difference between 21.4 Celsius and 16.2 degrees Celsius. This difference right here is 5.2 degrees Celsius. We're limited to two significant figures here, so our heat is 1700 joules, and this is a positive. The process of dissolution of this potassium nitrate salt is endothermic. Heat went from the surroundings, the water, into the salt to dissolve it. We know this because the temperature of the solution decreased. The change in the enthalpy should be reported as a positive value. This is also positive 1.7 kilojoules. I'll convert the mass of the potassium nitrate into moles of potassium nitrate using its molar mass. To four significant figures, this is 0.04952 mole of KNO3. So, our delta H of hydration is a positive 1.7 kilojoules for every 0.04952 mole. To two significant figures, this is 34 positive kilojoules per mole. From the literature, we know that the accepted value is 34.9 kilojoules per mole, so we can get a percent error here. It's the difference times 100. And to correct significant figures, this 0.9 should be rounded up to 1. When we subtract, we want fewest decimal places, so this is a 0, and then the next number tells us to round up. That's just 1. And to one significant figure, this is an error of 3%. So again, this is reasonable.